Hey, welcome back. In this topic, we're going to talk about differentiating between atoms. We're going to talk about what makes one atom different from another. You remember your atom, right? The nucleus in the middle, which contains your positively charged protons and your neutral neutrons, and then orbiting around the outside in your shells, we have those negatively charged electrons. So we're going to talk about why one atom is different from another. I am pretty sure you may have jumped ahead a bit and thought to yourself, it's probably got to do with the number of protons or neutrons or electrons that we have. And you're absolutely right. So let's have a look at how this changes our atom, and let's talk about how we speak chemists, how we communicate this information from one person to another. So we are going to need our periodic tables for this challenge. Once again, make sure you've got it nearby. It's in the additional resources area if you've lost your last one, but it's essential. We're not getting anywhere without it. So, when chemists are talking about an atom with one another, we will often represent it in this AZX structure in order to provide as much information as possible about the atom we're discussing. So let's talk about these three different components, one at a time. We'll start with the easy one. We're going to start with X. X is the atomic symbol, so it tells us what type of atom or what type of element that we're talking about. So if you have a look at your periodic table, if I take element number 1 up in the top left corner, that's hydrogen. It has the atomic symbol H. If we pick a different element, if I pick element number 7, so over to the right hand side of your table, that's element nitrogen, that has the symbol N. You'll notice on your periodic table that quite a lot of them have 2 or even 3 letters at times representing the element. When we do that, it doesn't change much. So if I head to element number 29 in the middle, we have copper. You'll notice that the first letter for copper is capital C and the second letter is lowercase u. So the first letter is always capitalized, the one that follows up is always lowercase. Now this is important, you need to remember this so that we can clearly distinguish when one element ends and another one begins. In fact, I have a little story for you about that. A couple of years ago, I was at a friend's place with a group of friends. I'm still good friends with a lot of people I studied chemistry and biochemistry and things with. But my best friend, he's a finance guy, so doesn't know a bar of chemistry. And we had a couple of drinks together, open up the drink, and there's a trivia question at the bottom of the cap. And it says, so in chemistry, what is CO? And we had a look at this, and of course, all being chemists and biochemists, we said, too easy, give it to the finance guy. So we gave it to him, he had a few guesses, had absolutely no idea, and so we all told him, we said, it's carbon monoxide. And he said, okay, whatever. And he walked off and we were enjoying our afternoon, and all of a sudden we hear from the other end of the house, you lied to me. We thought, what on earth is he talking about? And we went out there. He's found a periodic table on the wall. Yes, my friends are the kind of people who have periodic tables on their wall. And he'd looked through, and sure enough, he'd found element number 27. He'd found cobalt. So again, the case matters. Capital C, lowercase o, that's an element, that's cobalt. Capital C, capital O, now you're talking about 2 elements that you've joined together. You're talking about a compound. So case really matters. So we're comfortable with the symbol? Easy enough to follow? Let's move on to the next letter of our AZX system. This is perhaps the most important letter of this structure. We're going to talk about the Z. This is the atomic number of your atom. This is really important to us. The atomic number tells you the number of protons that there are in your atom. And this is important because the number of protons defines what element you have. Have a quick look at your periodic table, or the example I've got here for you. If I take an element tile off your periodic table, I've got hydrogen shown here. Up in the top left corner you can see the blue number 1. That is the atomic number for this element. That tells you the number of protons that are present in the nucleus. And once again, it's important because it defines the element. This element here, it has 1 proton. That's what makes it hydrogen, the fact that it has just 1 single proton. Let's go through a couple of examples. Watch it evolve, see if it will help this come clear. I've got an atom here for you on the screen. Have a look, count up the number of red positively charged protons in the middle. I'm hoping, if your maths is the same as mine, you're going to find 6 protons in the center there. Have a look at your periodic table. Find the element which has 6 protons. You'll find that it's carbon. Any atom that has 6 protons in the middle, by definition, will be carbon. What if I make a change to that? What if I add another proton? Now we've got 7 protons, it's not carbon anymore. Now it's nitrogen. What if you added another proton? Well, we're not at 7 anymore, we're now up to 8. Element number 8 on your periodic table, you now have oxygen. What if you added a lot more? What if you add another dozen? Now we're up to 20 protons in the middle. Check your periodic table. Any atom that has 20 protons in the middle must be calcium. So again, really important, the number of protons in the nucleus define what element you have. Really useful for us. Comfy? All right, let's move on to the final of those three letters that we use to denote an atom. Let's move on to the letter A up there. A we refer to as the mass number of the atom, and it tells us the number of protons and neutrons combined within the nucleus, the mass number. Let's have a look at a couple of examples to help us get an idea of this. Here I have a chlorine atom. I'll save you counting the protons. So it's chlorine. Check your periodic table. By definition, chlorine has 17 protons. It will have 17 electrons with a negative charge to go with those 17 protons. But what I want to focus on is the neutrons. It has 18 neutrons. If you add 17 and 18 together, you get 35. So the mass number for this chlorine atom would be 35. If we were drawing our AZX structure, we'd start with the symbol. For chlorine, that's Cl. We then put in the atomic number down the bottom. It's chlorine, has 17 protons, it must have, and therefore 17 is your atomic number. And up the top, the mass number, protons and neutrons, 17 plus 18 is 35. So this is our chlorine atom. Now we're going to look at another chlorine atom, but with a small change. So here we are once again, chlorine with 17 protons, that's what makes it chlorine, and 17 electrons to balance out those 17 protons. But this time it has 20 neutrons. So if we were drawing up our AZX structure for this atom, we would put once again Cl as our elemental symbol for chlorine. Once again it's chlorine, so we must have 17 protons. That makes it chlorine. And our mass number, our number of protons, 17, plus our neutrons, 20, that adds up to 37. So that will be how we would describe this chlorine atom. If I put those two atoms side by side now, we can get into some of the lingo. We actually name these elements by their mass number. So I would call the first one chlorine 35, and I would call the second one chlorine 37. And these are what we call two isotopes of chlorine. An isotope is what you have when you have an atom which is the same element, so the same number of protons, but just differing numbers of neutrons inside the nucleus of that atom. Now we've covered A, Z and X, and we've talked about protons and neutrons. What about the electrons? Why don't they get a mention? Well, the best way I can answer that question for you, have a look around you. Try and find something that's charged. Try and find something that isn't neutral overall. Maybe you found your pen. Maybe you found your drink. Maybe you found what's left of your breakfast. Regardless of what you found, I'm pretty sure you're going to find that it has no overall charge, that it's neutral overall. One of the better challenges that I've had from my students in recent years about this idea is the idea of static electricity. But as you can see, even static electricity doesn't want to be there and will do whatever it can to get rid of itself. So, what does this mean about our electrons? Why haven't we shown them in our AZX structure? If our atom's going to be neutral, then the number of negatively charged electrons has to be the same as the number of positively charged protons. And that's the way they live. What happens when that's not the case? Well, that'll be a big part of what we do in Module 2 in this subject. So let's recap where we're at today. We've had another look at our atom. We know a bit more about our positively charged protons, our neutral neutrons, and our negatively charged electrons. We've used the AZX model to allow us to describe an atom from one chemist to another. And of key importance, those protons, remember that they define the element that you're looking at. Again, if we go back to your periodic table, if we pick an element out of it, for example, element number 16, the element that has 16 protons will be sulfur. It will be that material. If I was to pick a different element from a periodic table, for example, element number 30, any element with 30 protons will be zinc metal. The 30 protons, that's what makes it zinc.